Hey guys, welcome back to AlgoYogi. Since we have already started graph series, it's really important that we study Dijkstra algorithm. Now, Dijkstra algorithm is used to find the shortest path from the source vertex to all the other vertices. Here I have drawn a directed graph that has basically 6 vertices from A to F, and then all the edges right here, they have their particular weight assigned, so which is kind of a cost from going vertex A to vertex B, or you can say in general vertex U to V. That's how we study in graph theory. Now, in Dijkstra algorithm, we will be basically using Min-Heap. I have already uploaded a video on Min-Heap, DFS, VFS, and like covering a little bit of Dijkstra algorithm, just a dry run. Here we will be doing a dry run as well as the code, a pseudocode that we will be using in all the, not all, but like most of the problems that require Dijkstra algorithm. Now, let's see what we actually do in Dijkstra algorithms. As I said, it's about finding the shortest path from the source vertex to all the other vertices from the source vertex. So if there are other vertices that are not reachable by the source, then they will have the shortest path as assigned infinity, which means you can't reach there, or -1, whatever you guys want, feel comfortable, or whatever you guys have studied. Like different graph stories have different, so all of these conventions. But here we will assign it infinity. Okay. So we don't have a source right here. Let's assign a source. Let's have a source. So we will call A as our source vertex. So our source, oh my god. Okay. So our source vertex, source is going to be A. So A is my source vertex. So that means we will be going from A to all the other vertices like here. So first we're going to visit A, and then from there we're going to start visiting all the other vertices. Now, since we have chosen our source already, which is A, so finally what we really calculate is this distance array that will actually store the distance from A to all the other vertices, or the shortest path, or cost, whatever you guys want to call it, minimum cost, minimum shortest path, whatever. Now, like from A to A, let's fill it up. Like in the beginning we do the initial assignments of like filling this distance array from A to all the nodes. So from A to A, basically it has, like, 0 distance to itself. Then B, so initially I'm going to fill it all with infinity, and then I will start my algorithm. So initially my min-heap priority queue, I will insert my source node into it. So the key here is going to be the distance, which is 0 from A to A, 0, right? And then the node itself, which is A. Now the algorithm starts with the while loop. As you know, we are using BFS here. So we will be visiting all the neighboring nodes of A, and then calculating the shortest path from A to its vertices, right? It's neighboring vertices. So let's pop out. We'll be asking, hey, min-heap or priority queue, give me your most prioritized node that I need to visit. So it will give me that it's the only node right now, which is the source node A, that has the distance 0 to itself. Now let's start visiting A. So I'll be asking using a for loop. Okay, remember that I'm already telling you guys like what we will be doing, that while min-heap is not empty, now I will be using a for loop on A to visit all its neighboring vertices. So you should be imagining basically the pseudocode already, but we will be writing the pseudocode for making things easy for ourselves later. Okay, let's visit all the neighbors of our node A. So the first node I see is B. Let's visit B. Now there is a direct path from A to B. So what I'll do is I will update this infinity with 2, because there is a direct path. All right, there is a direct path, so I'm going to update it with, because 2 is less than infinity, so and there is a direct path, so I can reach B with the distance 2. Then at the same time I will append that 2 as a distance and B as a node into my minimum heap. Okay, then what's the next node? The node is C. So C has infinity distance, current distance is infinity. That means it's not reachable, but there is a direct path. There is a direct path that has the distance 4. So I will assign 4 here, because 4 is smaller than infinity. All right, 4 right here, and then I will also append it to my min-heap. So the distance is 4, and my current node is C. Now there is no neighboring node from A. We have already visited all the nodes that we could visit from this directed in this directed graph from A to all its neighboring nodes. So what do? We are done visiting A. We're done visiting A. Now let's pop the next node that we want to visit. So here you can see that this priority queue will give me, I will ask like, hey Min-Heap, give me your most prioritized node that I need to visit. So it will give me because it's a Min-Heap, and its key is the distance. So it will, what is the shortest distance right here? It's 2, and 2 has the node B. So I will be visiting B. So I will pop this B out, and this is the node that I'll be visiting now. What are the neighboring nodes of B? I'm going to just write them here. So neighboring nodes of NEIGH, all the neighboring nodes of B are C and then D. Now C already has a distance because it was directly reachable by A. But the point here is we are performing the relaxation right here. So relaxation means the direct distance from A to C is 4. But there is an indirect distance from A through B to C, which has the cost. There is already cost 2 to reach B, and then one more distance. So 2 plus 1, that is 3, and this 3 is less than 4. So I will update the distance here from A to C, this 4, with 3. All right, with 3. So I will update this. So I'm currently visiting C. I'm not visiting, but I'm just like calculating the shortest distance from B to C. Okay, so I will update this with 3. You already know why this I'm updating it, because 2 plus 3 is less than 4. 2 plus 1 is less than 4. 3 is less than 4. Okay, now this I'm done. But remember that I will now be adding that. To my so I'm not really adding it. I will be basically updating what I've already added it here. Okay, so this will become now 3 and C. Now this C is already gone. Now I'll come to D. I'm right here. So what is the distance right now in my distance array? It's infinity. So I will update this with 7 plus 2. 7 plus 2 is 9, and then I will append that to my priority queue, 9 and D. Now I'm done visiting B. Sorry, I should not remove this, maybe just this. So I will pop the minimum element, which is this, and then I will start visiting C. So let's visit C. C has only one neighbor, which is E. So only one neighbor, which is E. So I'll write that down. Now let's see what is the distance of E in my table, which is infinity. But I can tell that to reach E. So let's write these short distances. From A to A is 0. I'm going to write in a different color. So let's call it A to A is 0. Then A to B is 2. I'm referring it from the table, by the way. C is 3. So here, when I'm visiting E, I will ask the distance to C itself, that cost, and then the distance from C to E is also 3. So this 6 is less than infinity. So I will update that. I will update this infinity. So 6, and then I will also append that to my priority queue, which is E. Okay, now I'm done visiting all the neighbors of this. So let's remove this. Then I'm going to pop the next element. Right now the value 6 is smaller than 9, so I'll pop E. I will pop E. Okay, what are the neighbors of E? D and F. So let's write D. And F. Let's start visiting D. D is already visited. That has a distance of 9 that you can see right here. Okay, so what's the distance if we were going to D through E? Because right now we are visiting E, but D is already visited through B. So this right here, we have already visited it, but then there is another indirect visit to it from A, C, E, and D. So the distance to reach D through E and C is going to be 3 plus 6 plus 2, which is 9. 9 plus 2 is 11. So that is basically greater than the distance that it already has, which is 9. So we're going to leave it that way. So we're done visiting this. So I'm going to remove D. Then let's see let's visit f. F is not visited, its distance is right now infinity. So what I'll do is 6 plus 5 is 11. 11 is less than infinity, so I will add 11 right here. 11 right here. Let's use the same color that we are using, 11 right here, and then we will also append f to my priority queue. Okay, now this we have also visited E. Okay, now what's the next node that I'll be popping? And we will keep doing it. We have right now visited all the nodes, but we're going to keep doing it until my Min-Heap is, or priority queue is empty. Next node that I'll be popping out is going to be 9 and D. 9 and D. So what are the neighbors of D? The neighbors of D is just F. Just F. Okay, just F. What was the distance that we calculated for D? That was 2 plus 7 was 9. That is already right here, and E is 6. So, and now I'm visiting D. I'm visiting D. So the neighbor of D is F. What is the distance that already present? That is 11. How about the distance through D? Distance through D. So right now the distance is already 11, but 9 plus 1 is 10. 10 is less than 11, so I'm going to update this. I'm going to update this with 10, and this also becomes updated 10. Okay, now this is done visiting. I'm not going to append F anymore because F is already present, but this distance has been updated to 10. Okay, now what I'll do, I'll pop this out, not like this. So I'll pop the last remaining node in my priority queue, F. F does not have a neighbor, so let's done visiting this. We are done visiting the entire node, and this is final distance, shortest distance array that we have just found out. So this is basically our answer. This is what the Dijkstra algorithm returns to us. Okay, that was the diagram. I hope that was pretty clear. Now let's write down the code. Let's write down the code. It was pseudocode I'll be writing. Okay, so I'm just gonna remove this for now and basically make it a little small. Okay, and probably let's just shift it to this corner. Let's write our code. So as I said, we will have basically a dictionary that will be the distance, right? That will be the distance. I'll have an assignment. I will use a default dict. I'm going to write this pseudocode like in terms of the Python. It's going to be super clear, but you can definitely like convert that to other languages. Okay, since it's going to be close to pseudocode. Okay, so let's say first thing first, we're going to have this distance array or dictionary, you can call it. This dictionary is going to be first. It's going to have the node. And next to node, it's going to have basically like I'm gonna assign infinity. Okay, so infinity for all the nodes. Okay, in graph. All right, so that's it. Now to begin with, we are going to have a Min-Heap, but also let's reassign this start node. So dist of start node is going to be 0 because distance of itself, the source node, which is start node, is 0. Then we're going to have Min-Heap. This Min-Heap is going to be basically initially it will be the distance, the key 0, and then the start node. All right, I'm writing it like in a general view. This start could be replaced with a. Okay, then as we said, like we're going to have a while loop while Min-Heap. What do? We're going to pop the most prioritized element, and let's pop it out as first going to be the current distance, and then the node, or you can call it current node, whatever you guys want to call it. And then this Min-Heap that we have, first we're going to heapify. So heap q, that is the library that we will be importing, and then heap pop. So first it will heapify this array that we just created, this array. It will heapify that, and then it will pop from the Min-Heap. Okay, and it will be giving me the most priorities or the minimum element. Then let's so what do we do here? Like we have the current distance and the current node that we want to find out the neighbors. But if skip it, if we already found a better path, So how are we going to skip it? So if the current distance is greater than the distance that is already stored in my this distance, because I have already found a better path, then I will continue. Okay, so if this current distance is already greater than my in the array dist for that particular node, I'm gonna, so that current node, or we have just written node. Oh my god, why have I written node? If this is the case, then just continue. Okay, continue. Otherwise, we're gonna visit all the neighbors of for n in the neighbors of this n in how do I find out? Like I can just call it neigh, neighbors of this node, and this will give me all the neighbors of this node. Okay, now here let's calculate the distance. So distance is going to be the distance of this current distance of this node from the source that was just like we found out right here, this current distance. So cur distance plus basically the edge that's going from my current node to the neighbor. So basically this is what I'm talking about. So node, which is u, to v, which is this neighbor n. Okay, and this edge is the cost. This is the cost. This is what I'm talking about. Oh my god, this is what I'm talking about. This is what I'm talking about, and that will come from basically the distance, that will come from the weight that will be given to us. I guess like it will come here with this. It will come with the neighbor. Okay, so n and w in neighbor. So I'll just call it w. So if this distance is less than the distance of neighbor that is in my array or dictionary. So neighbor, I should not write it neighbor, just n. If this is the case, then I will be updating my dist for that n, and then I will assign this distance. Okay, at the same time I will add that to my min heap. So heap q dot heap push. So this is basically I'm writing in perspective of Python. So heap push min heap. Where are you pushing? Into my min heap. That's how you do it. And then what are you pushing? The value that is the distance I just calculated for my neighbor n. Okay, so I'll just write it like this is this, and then finally remove that. Okay, now I think that's the entire solution, and then finally you can return, and I should like maybe return this distance. Okay, so this is the entire code, guys, for the Dijkstra algorithm, and we will be using it like throughout most of the series in a lot of problems. So alright, see you in the next problem of LeetCode.